Hi, I'm Tianqi from the Institute for Interdisciplinary Information Sciences at Tsinghua University. I'm glad to share my recent work with Jiatu on the explicit circuit lower bounds. Our talk will have 4 parts. We'll first introduce the background and history of this puzzle and state our main results, and then I will briefly give you a proof sketch of the previous 3.1/86 n minus little n lower bound and introduce this basic technique, which is the gate elimination paradigm, and then I will show how we improve over the results and get the 3.1 n minus little n lower bound. Finally, I will present some open problems. Let's first briefly review the main computational model we are interested in, circuits. Throughout this talk, we are focused on the so-called B2 circuits. That is, each gate in the circuit has in degree 2, exactly 2, and the gate can compute an arbitrary binary function. So each gate can not only compute an AND or OR, but can also compute other functions like parity and NAND or other weird functions. That's okay as long as it is binary. And we measure the circuit size by the number of gates in it, and that includes all the input variables. So the circuit here has circuit size 4. Note that we only focus on single output functions, so our circuits should have a single output gate. This is an example of how we evaluate the circuit. The main question we are interested in is what is the power of circuits? Textbook result tells us that each Boolean function can be recognized by a CNF, and a counting argument by Shannon shows that a random function requires circuits of size omega 2 to the n over n with high probability. Improving on these results, Lupanen showed by a more sophisticated analysis that the upper and lower bound can be made rather tight. The upper bound is as low as 1 plus little o 1 times 2 to the n minus n for every Boolean function. And for almost all functions, they need a circle of size at least 2 to the n minus n. This is a very tight upper and lower bound. But this lower bound is not constructive. We cannot find a certain simple function satisfying this lower bound. And indeed, for most common functions, such as the majority function, they should have very small circuit complexity. So this lower bound is not that useful in this sense. So let's try again. We take a language L from deterministic time TL. Another textbook result tells us that the same language L is computable by circuits of size T log T. So we know that every language in P has polynomial size circuits. It is contained in the class P/poly, which is the class of languages computable by polynomial size circuits. But what does if we replace the class P by NP? What we believe is NP is not contained in P/poly. Indeed, this follows from if you believe the polynomial hierarchy does not collapse. So this NP is not contained in P/poly is a statement we believe, and it is interesting enough to imply P is not equal to NP. So this is one of the most interesting and major open problems in circuit complexity. However, this problem turns out to be very hard. So we believe that there exists a function in NP not having polynomial size circuits, we are even far from proving the existence of an NP function not having circuits of size, say, 5n. This figure shows the efforts people have been made to attack this problem. The race originated from a work by Close and Merishev, who proved roughly a 2n lower bound for some function in P. Another 2n lower bound was given by Schnorr. Some years later, Stockmeyer and Paul independently gave 2.5n lower bounds, and the later one was improved to 3n by Blum in 1984. This 3n lower bound stayed unbeaten for over 30 years, and it looked like it was really hard to even improve this lower bound a little bit. It was not until 2016 when Fine, Goldner, Hirsch, and Kulikov proved a 3 plus 1/86 n minus little n lower bound, following another 3n proof in 2011 for a new hot function. This is a breakthrough in this line of work. What we do is to further improve upon this 3 plus y over 86 and lower bound, and show that some function in P requires circuits of size 3.1n minus little n. It is worth mentioning that all the hard functions before blob already have linear size circuits, so you should not expect a superlinear lower bound using them. However, the proof in 2011 gave a new hard function, affine dispersal, which is also a function we used in this work. We define it formally later. This new function is not known to have linear size constructions, so theoretically we can expect a superlinear lower bound using it, right? But still, we don't know how to prove it. Here we also mention a related line of work. Recall that our circuit model can have gates computing arbitrary functions. But what if it disallows the usage of linear gates, that is, parity and equivalence? This is a circuit model called U2. U2 circuit lower bounds have also received much attention, and the best result currently is a 5n lower bound proved 20 years ago. So you can see that in either B2 or U2 case, even proving a small linear size lower bound is quite hard despite much effort. So why do we care about circuit lower bounds? Apart from the implication on P versus NP which we discussed earlier, circuit lower bounds also have implications to other problems in structural complexity, derandomization, cryptography, and many other topics in computational complexity. So circuit lower bound is actually a central topic to study with. Now, I will move on to talk about the previous 3 plus 1 over 86 and lower bound, and prepare for a later discussion on how we improve on it. The main weapon to prove such unconditional lower bounds for general circuits is gate elimination. Essentially, this is the only weapon up to now to attack this problem. First, we assume some hard function f, and we know that some circuit C computes this function. What we do is to do some restriction on this function. For example, we let the first input to be 0. We call this restriction R1, and we get a restricted function f restricted to R1. And now we can transform the original circuit C to some other, might be simpler circuit C restricted to R1, computing this restricted function. We do this process again and again, and we repeat it little r times, and we get a function f final and a new circuit C final. We argue two things. First, f final is still not a constant after all these R restrictions. Second, at each such restriction, we can always somehow eliminate at least delta gates from the circuit. That is, for example, the circuit C restricted to R1 is at least delta smaller than the original circuit C. If we can prove these two statements, then we can directly imply that f requires delta times r gates. A toy example. Take the hard function parity, and we do a constant substitution at each time. Obviously, the parity function is still not a constant after n minus 1 constant substitutions, and we can observe that we can eliminate at least one gate per restriction. Why? The gate directly fed by the restricted input will only depend on one of these inputs by then, for example this gate. Then we can remove the gate and rewire the circuit as shown by this example. So we can conclude that the parity function requires at least n minus 1 gates to compute it. But parity cannot give us a better lower bound because it can obviously be computed by a circuit of size n minus 1. So the idea is to extend the hard function. We define the affine dispersal for sublinear dimensions to be the functions that are not trivial if the inputs are restricted to an affine subspace of little n dimensions. This allows us to perform n minus little n affine substitutions of this form. For example, x1 equals to x2, xor x4, xor x5, xor 1. And after all these n minus 1 affine substitutions, the function is still not constant. And we already know that such affine dispersal has constructions in P. So our idea is to somehow do constant substitution and affine substitution, and ideally we wish to eliminate 4 gates per substitution. This will yield a 4n minus little n lower bound. By plugging this idea into the framework before, we have this figure. Now the hard function is Fn disperser, and we do Fn substitution at each time. The hard function is not trivial after n minus little n restrictions, and our goal is to eliminate 4 gates per restriction, and this will give us a 4n minus little n lower bound. Now let's give a try. Consider the topologically minimal n-type gate. For n-type, we mean gates computing some projective function, and by XOR type, we mean gates computing some linear function. There are several cases around this n-type gate. As an example, we can consider this figure. This gives a particular example of how the local topology around the topologically minimal n-type gate can look like. In this case, we can do a constant substitution to x1 and make this n-type gate trivial. By trivial, we mean the gate computes some constant function. And in addition, we can see that these 3 dashed gates will become only depending on one of their inputs. We call them degenerate. This is because these 2 gates are constant, so they only depend on their other inputs. And we can see that they can clearly be removed from the circuits with certain rewiring. In this case, we can eliminate 4 gates, 1 trivial and 3 degenerate, so it is an easy case. Similarly, you can show that this is also an easy case. In this case, we can again do a constant substitution to x1 to make this n-type gate trivial. The key is this x2 will become of odd degree 0. We argue that this can only happen for sublinear times, or these isolated variables will already form a subspace making the Fn disperser constant. So this case is easy as well. For this last case, it is not that easy. If we directly apply the method before, there are only 3 gates to be eliminated. We'll talk about this case later. In the previous slide, we only considered substituting to a variable, but we can't do so if the n-type gate is fed by some XOR type gate. Fortunately, this can still be done with some effort, but here we do not go into the details, so let's take it as a magic. That is, for an XOR type gate with no n-type ascendant, we can somehow do an Fn substitution and proper rewiring on the circuit to make it constant. And this does not increase the size of the circuit. Note that the XOR type gates cannot have n-type ascendants. This is quite intuitive, since only then the gate computes some linear function on the input variables. And this is exactly why we consider the topologically minimal n-type gate. By the topologically minimality, any XOR type gates feeding them should not have n-type ascendants, since it is topologically minimal. With the magic, we can show that all these 2 cases can be handled while eliminating 4 gates, so they are all easy. After considering all these cases, there's only one more trouble, this case. This is the only case left unsolved. We can only eliminate 3 gates using previous arguments. So one of the key ideas in the FGHK paper in 2016 is, instead of directly attacking this case, we apply amortized analysis on this structure, on the number of this structure, which we call trouble gate. We define the complexity measure of a circuit as the number of gates plus the number of trouble gates times some constant alpha t. The exact value of alpha t will be given later. And during the gate elimination procedure, we argue the decrement of complexity measure instead of directly arguing on the number of gates. The key observation is 2 facts. First, there are at most n over 2 trouble gates in the original circuit. Second, the elimination of each gate will only introduce at most 4 trouble gates. these two facts, what can we do? We can see that with the second fact, we can say that in all the previous easy cases, we eliminate 4 gates while introducing at most 16 trouble gates. This will decrease the complexity measure by 4 minus 16 alpha t. And if we can additionally argue that we can eliminate the trouble gate without introducing any other new trouble gates, we can decrease the complexity measure by 3 plus alpha t. That's because by eliminating a trouble gate, we can remove 3 gates from the circuit, and if we do not introduce any new trouble gate, we can further decrease the complexity measure by alpha t. So we, in total, decrease the complexity measure by 3 plus alpha t. If this can be done, then we can let alpha t to be the constant maximizing both these two values, and we can argue that initially the number of gates must be greater than 3 plus 1 over 34 minus little n. But this lower bound is only true when we can prove this statement. We can eliminate the trouble gate without introducing new ones. In fact, this can be done with a careful case analysis, except this particular case. This case is a bit complicated, but it is the only case which prevents us from proving this statement. So how do we handle this case? We can see that if we can additionally do quadratic substitutions of this form, we know that it can be resolved. We can, for example, let t equals x1, x or some constant c1, and x2, x or some constant c2, x or c3, and we can carefully choose c1, c2, and c3, such as this XOR gate is constant, and the constant can be set properly to make this following n-type gates constant. And by making these two gates constant, these two dashed gates becomes degenerate. And we notice that in addition, this AND gate now has odd degree 0, so it can also be removed. In this case, we remove 5 gates from the circuit. That's an overkill. But the problem is, we don't have explicit constructions for quadratic dispersers, which allow us to do quadratic substitutions. How do we solve this? The solution is we allow some kind of temporary quadratic substitution, which is enough to solve this case, and it is so temporary that only Fn disperser is enough for us to argue the lower bound. This is a bit complicated. You can see the paper in 2016 for details. But anyway, in this way, and by extending the complexity measure and adding more case analysis, we are able to get a 3 plus 1 over 86 and minus little n lower bound. This is the idea behind FGHK to get a 3 plus 1 over 86 and lower bound. So how do we make it 3.1? To improve it, we first ask ourselves, what makes the advantage only 1 over 86 in the previous argument? It is because the number of trouble gates introduced is too large. So, can we give a better bound on the number of trouble gates introduced? To reduce the number of trouble gates introduced, we first examine where the 4 trouble gates at each elimination come from. Here is one of the extreme cases where the trivialization of the middle n-type gate will produce 4 new trouble gates. But we can observe that instead of getting 4 independent trouble gates, we actually get 2 pairs of trouble gates. So we now study this pair of adjacent trouble gates more seriously. We can more or less easily see that this is actually an easy case. We can, for example, do constant substitution to x1 and x3 to make these two n-type gates trivial, and in such case, the middle x2 variable will become of odd degree 0, which we have already argued that this will not happen for more than some linear times. So, although a single trouble gate is hard to handle with, two adjacent trouble gates become easy to eliminate. We call this structure trouble pair. Now returning to this figure, the trivialization of the middle and n-type gates will now introduce two trouble pairs instead of four trouble gates, and the trouble pairs do not bother us. And other cases where four trouble gates are introduced have similar properties. So our first observation is the elimination of each gate will only introduce at most two truly trouble gates. By truly trouble gates, we mean those having no adjacent other trouble gates. And we can see that at most one introduced by each of the incoming edge of the eliminated gate. That is, for this eliminated gate, each of its incoming edge will only contribute at most one truly trouble gate. By reducing the number of trouble gates introduced to 2 is still not enough. Our second observation is that in most cases, the gates eliminated at each substitution form a connected block. For example, this is the case we considered earlier. We do a constant substitution to x1 to make this n-type gate trivial and first making the following 3 gates degenerate, these 3 ones. And you can see that all these gates are connected. How can this help? For each edge within this block, such as the red edges here, one can see that they will not contribute trouble gates. For example, in this figure, that's because x1 and this AND gates are already eliminated from the circuit. So, for gates in such a connected part, the elimination of each gate will only introduce one truly trouble gate, because one of its incoming edge is within this connected block. This is summarized in formula as such a fact. For a connected part to be eliminated, in most of the cases, each gate only introduces one new truly trouble gate. So with these two observations in mind, we now try to improve the previous bound. Remember the two cases we said previously on the decrement of complexity measure. One case remained the same. We eliminate a trouble gate without introducing new trouble gates. The second case, we eliminated 4 gates. And now, instead of introducing 16 trouble gates, we are able to argue that only 4 ones can be introduced. So we can decrease the complexity measure by 4 minus 4 alpha t now. In such case, by plugging the alternative 4, we can get a 3.1 n minus little n lower bound. But there's still some technical issues. Remember that we have mentioned an even harder case where we cannot eliminate the trouble gate without introducing new ones. In FGHK, we use temporary quadratic substitution to handle them. This results in two more cases. We either eliminate 7 gates by 2 subsequent substitutions, and by our 2 observations, it introduces 7 new trouble gates, or we eliminate 10 gates by 3 substitutions and introduces 10 trouble gates. With these 2 cases, we can only get a 3 plus 1 over 26 minus little n lower bound, which is a bit weaker than the 3.1 and we wish to prove. So we need to improve these 2 cases. These 2 bottleneck cases. This comes to our final observation. In the bottleneck cases, the structure is so specific that we can further use their local properties to reduce the number of trouble gates introduced. For example, recall this case where we do temporary quadratic substitutions. Here we do a quadratic substitution to make this XOR type gate and this N type gate trivial, and this following 2 gates degenerates, and this AND gate of our degree 0. In fact, we observe that throughout this process, only the elimination of these particular gates can introduce trouble gates via lots of case analysis. Similarly, when we later kill the temporary quadratic substitutions, we also use lots of case analysis to remove the number of trouble gates introduced. So with this case analysis, we are able to reduce this 7 and 10 to 2, and this is enough to make a 3.1 minus little n lower bound. So in summary, we first generally reduce the number of trouble gates introduced while eliminating a gate to 1, then resolve these two bottleneck cases to achieve our desired lower bound. Finally, let's talk about some open problems. First is some technical open problems related to our results. Recall that we talked about the 5n minus little n lower bound for circuits without linear gates. Can we use the methods in FGHK and our improvements to give a better lower bound in this setting? And can we give a tight barrier that the current analysis cannot give better results than 3.1n minus little n? Note that the barrier is already known for gate elimination, that superlinear lower bounds are not likely to be proved. But can we make the barrier tight to 3.1? On the other side, can we construct FN dispersers in linear circuit size? This problem has independent interest in the theory of extractors. And can we construct strong enough quadratic dispersers with polynomial sized circuits? This can be used to imply a 3.11 and lower bound by GK16. Finally, is this proof using gate elimination natural in the sense of Rasbrov and Rudish? This is a problem I personally very interested in, since the procedure of gate elimination seems to heavily use the structure of the circuits, which does not seem to be natural. That's all. Thank you very much.